Hello everyone, my name is Carlos Latorre and I am pleased to present this project conducted in collaboration with my colleagues Gilberto Juárez Rangel and our advisor Francisco Delgado, all from the Tecnológico de Monterrey. Today we will walk you through our research on quantum key agreement protocols, aiming to improve cryptographic security by incorporating quantum mechanics. In today's video, we will discuss the following points: our objective, which is our main goal in this research, the preliminaries, which is an overview of the fundamental protocols, the quantum key agreement protocol, and EBB84 protocol, which is an enhancement made over BB84, our proposed quantum key agreement code, security analysis, quantum fidelity, the failure probabilities for an event of an attack, and multi-party version, and our conclusions. So our objective is to develop an indefinite quantum key agreement model that is robust against eavesdropping attacks. The model leverages the principles of quantum mechanics to allow secure multi-party key generations without relying on prior agreements between participants.
Well, the first of the preliminaries are the quantum key agreement protocol, which is pretty much the same as the quantum key distribution, where we have two or more parties that are trying to use quantum computing to share a cryptographic key. Additionally, on the quantum key agreement case, we established that none of the participants has control over the key. This will lead to further results.
Now we have the EBB84 protocol, which is an enhancement of the well-known BB84 quantum key distribution protocol, but without requiring a classical channel of communication for basis reconciliation. So these improvements make it more secure by reducing the exposure of data in potential vulnerable channels.
And in here we have the quantum key agreement code that we propose. On the right top hand side, we can see the quantum circuit diagram that shows the protocol. We have 5 registers, which involve C, Charlie, which just interacts in the system, but it's not a transmitter nor a receiver. Alice, which is the transmitter, has A1 and A2. A1 corresponds to a qubit that is going to be sent to Bob, and B1 belongs to a qubit of Bob that is going to be sent to Alice. And B2 is A2 and B2 are just the qubits that are going to stay static with Alice and Bob. In here we can see that we separated the circuit in 3 different steps. On the first steps, we have the interaction of Charlie's qubit, which is on an arbitrary state by using the control Hadamard gate. Once this is done, we utilize CNOT gates from the qubits that are going to be sent as the controls to the static qubits as the targets. Finally, on the third step, Alice and Bob receive the qubits and apply again the CNOT, having the A2 and B2 as the targets. In here, we can see that the final state on either measurement done on the computational basis on A1, B1, or C will lead to the semi-cryptographic key for A2 and B2. This means that the key is indeterminate and will be shared without being established by none of the participants.
Now we have the intercept-resend attack. This is not secure. And this happens when an eavesdropper intercepts the quantum transmission between two parties, in this case, Alice and Bob, measures the qubits, and then resends them. In a traditional protocol like BB84, which only involves Alice and Bob, this attack can compromise security, as the eavesdropper can alter the data without being noticed in some cases. So with the addition of our third party, Charlie, we can eliminate this possibility. Our solution builds on the EBB84 protocol, which uses a shared key to determine the measurement basis in advance, eliminating the need for classical communication channels. This helps secure the protocol from an intercept-resend attack and significantly reduce the ability of an eavesdropper to remain undetected. Now we will talk about our security analysis. First, we need to talk about our quantum fidelity. This measures the similarity between the expected quantum state and the state after a possible eavesdropping attempt. In our protocol, the quantum fidelity decreases notably in the presence of an eavesdropper, making it easier to detect unauthorized interceptions. So this is a graph that demonstrates the fidelity as a function of alpha when theta is pi fourths, and it's between, well, it's either pi fourths or 3 pi over 4.
Additionally, we also use what is known as the eavesdropper failure probability, which corresponds to a probability for the detecting whether the eavesdropper receives the qubits, measures them, and sends them back again. On the right-hand side, we can see the results in 4 different equations for each of the cases of the choices of Alice above and the measurements obtained. In here, we can see the same 4 equations plotted on a surface graph. And on the right-hand side, we can see the average for the cases of theta between p-fourths and 3 p-fourths as a function of alpha. Moreover, we can also use the total probability failure, which can be obtained by adding the multiplication of the fidelity by the probability. And we can see here this mountain shape that we can obtain from the total probability for different values of theta 1 and theta 2. On the right-hand side, we can see specific cases for the difference between theta 1 and theta 2. And we can observe that on average, this approximates to a probability of 3/8 of failure for the eavesdropper. These results are good since for BB84, this is about 25%, and we are achieving a little bit further. Finally, we would like to add that this protocol can also be done for multiple participants by just rolling the qubits between them and applying the CNOT gates. This will accumulate the key on the ancilla qubits, and at the end, all of the participants will share the same key.
To conclude, we have proposed a quantum key agreement model that offers significant improvements in security over existing protocols by utilizing indefinite coding and an EBB84 foundation. We enhance resistance to intercept-resend attacks, and our protocol achieves low fidelities and high failure of probabilities for eavesdroppers, making it highly robust for secure communication. Thank you for your attention.